Okay, this problem was a classic statics problem. And statics means that the sum of the forces as a vector are 0, and the sum of the torques are also 0. So we had the problem of sitting, or standing maybe, on a big table. And the question was, how close to the edge can you sit? And so there's two different ways to do this. Well, there's two different things you have to write down, I should say. One is the sum of the forces, and the other is the sum of the torques. So if we start by drawing this as a free body diagram, say the table, there's the force of the person, let's call that mg. There's the force of gravity on the table, let's call that big mg. And then there's each of the legs. So say we can call that normal 1 and normal 2. So if we write down that the sum of the forces is, say, normal 1 plus normal 2 minus mg minus capital MG, and if it's all in equilibrium, that equals 0. Now when it starts to tip, that means that if it's going to tip over due to the weight of the person, if we call this leg 1 and this leg 2, it means that the normal force of 1 goes to 0. Well, that's interesting, but all we've now said is that the other leg at that moment is bearing the combination of the weight of the person and the table. So that's not terribly interesting until we write down the equation for the sum of the torques. So the sum of the torques, that's also equal to 0. And so you can pick the rotation around any point. So let's, just for fun, pick this point here to calculate the torque. And so we have, again, 4 different forces. The torque due to 1 is equal to, well, let's see. It's the distance between where the moment of rotation is to where the force is applied. Now you might think this has to be some sort of diagonal force, but no, it doesn't, because this is a cross product, so we need only the perpendicular component of distance with respect to the direction that the force is applied. And in this case, the force is applied upward. Okay, so the torque then due to force 1 is normal 1, and if we say the distance, say, from the center to each leg is d, then that means that it's n1 times d. The torque due to the person, say me, let's say now there's an additional distance x, and so my distance from the point of rotation, this one's still here, is going to be equal to my mass, mg, my force downward, times its moment arm, which is x. And the torque on the table, the gravity on the table, is equal to, well, now gravity acts at the center of mass of the table. So it's going to be capital mg times d. That's this distance here. So now we have to think about the signs, and if we choose that torque out of the board, which would give an angular acceleration this way, if we call that positive, then that means that the force of the one leg is negative, and then the force of gravity is positive on the table, and I am another force that's negative, or a torque that's negative. So what about tau 2? Well, that's why you pick a point where a force is applied, because what that means is that the force that's applied at the pivot point is like pushing on the hinges of a door. That torque is 0. So what we have left over then is the sum of the torques is equal to minus n1d minus mgx plus mgd, and that equals 0. So when it's tipping, that means that n1 is going to 0. The one leg is losing contact. Okay, So that means that m, and we'll cancel out the g's, is equal to m g d. And that's the answer. And what it basically says is that mx has to be equal to md. So if m equals m, that means that where you can sit, since gravity's pulling this way, is on an equal distance on the other side from the center of gravity. If m is really small, then x is large. So that means that if you're sitting on a huge chunk of rock table and you weigh very little, then you can sit wherever you want. But if m is large, then that means that x is small. You better be sitting very close to that. Oops, sorry, if m is small, meaning it's a table made out of cardboard, there we go, then x is small, meaning you better be sitting right on top of the leg. Okay.